Welcome back to our bats class. As always, let's start the day with some questions from our students that have been voted to the top here. So here's a question. Would a bat make any echolocation sounds if it were being chased by a predator? And what kinds of sounds would they make? Would they signal to other bats to run? Let's start off by thinking about what are the types of predators that might be attacking a bat, and how scared are they of them? So the first thing that we can do is we can say that, okay, well, one of the predators that we know eats bats is an owl. They can definitely do that. And so when you play the sound of an owl, here's that same question again, but let's just ask the sort of sub-question of what sort of predators might go after a bat? And if you're thinking birds of prey, perfect. You're looking for the night birds of prey, like, for example, an owl. So we've looked at some studies where people have played back the sounds of cicadas or played back the sounds of other bats to look at the reactions of bats. And so let's look at another one. Let's take the sounds of owls, and we'll play those for back out in the forest for a little while, really loud, so that definitely bats can hear them, and then record bats to see if their activity level changes. What these scientists did was they did this with a control situation where there was no recording played back. It was just the regular old bat activity, and they kind of got a baseline of bat activity. It's this blue bar with some error bars on it. You can see there's pretty big error bars. Sometimes the activity went down as low as almost zero, and sometimes it was twice as high. But this gives us a sense of the variation in activity. Then we play back, say, a great horned owl, or a barred owl, or a screech owl, or a random noise. And I want you to look at these here and try and decide, do you see a pattern? Is there any significant effect from playing the sounds of those voices? Hopefully, if you're looking at this, you're saying, well, if anything, the barred owl makes it look like it's more active at those times. It's attracted to the barred owl, but more likely we're just looking at random noise, and all of these here overlap within their error bars quite comfortably. So there's no significant difference that we see between these bats or between the bats when there's an owl sound or there's not an owl sound. So, okay, they don't seem to be scared by them. So when do they get attacked? And the answer is that birds of prey usually attack. They're more likely to attack near the roost. And so we've got a little video answer to that to watch a little bit about this before we start looking at their distress calls. And this is kind of providing us some of the context here.
Many red-tailed hawks stop for a bite to eat at Bracken Cave in southern Texas. High on the menu are 20 million free-tailed bats that have just arrived from Mexico to breed. It's the largest gathering of mammals on the planet. As the bats leave to feed each evening, they run the gauntlet of the waiting hunters. For a rookie hawk that's just arrived, they're quite a challenge. She has to learn how to catch them. But she's pitched against the fastest and most agile bats in the world. The sheer numbers are overwhelming, especially for a beginner. Finally, she spots a bat that's strayed from the mass and flicks her back claw to hook it. Impressive stuff, but nothing compared to the real Top Guns. these experienced hunters have learnt the best technique. Dive bombing the bats at over 160 kilometres an hour. The best can catch a bat with one talon while still holding another.
So I guess one of our main take-home messages from this is that birds of prey often are attacking near the roost. And so maybe that's why our bats are not concerned when they hear an owl out in nature. Now, another aspect of difference between this video here showing our raptors and owls is that owls often, when they're hunting, hunt very silently and sneak up on the bats, and so their calls that they make are territorial calls. And so a bat might not be worried about a territorial call because it's not necessarily indicative of whether or not an owl is going to attack them. It's more about where they are in the habitat they're in, and they might avoid places that that owls typically are, and that might be their way of protecting themselves from owls. So lots of different possibilities in there, but this little bit of information can help us understand about why they may not be concerned by the sounds of the owls when they're out and about. But I guess we should get back to our original question about if a bat were being pursued by a predator, would it scream? Now, bats do indeed make distress calls, and I'm going to play two sounds for you. One of them is a regular echolocation call, and one of them is a distress call. And I'd like you to try and see if you can hear the difference with just your ears. I'll do them again. Well, I'm not sure I can hear it just by itself, so maybe I'll add a little bit of visual stimulation as well. So the one on the left sounds like, and the one on the right. Well, we know from last time that calls that have a social component often go to lower frequencies because the lower frequencies travel further before they attenuate. So that might be part of the cue and clue in here. But there's also another aspect of this sonogram that I want you to take a look at here. You can see it kind of in this call right here, how there's some frequencies that have high and some that have low, and those vary as they go through. It's a little bit weird looking, and if you look at the another version of a sonogram, it kind of looks jagged. You can see these little spikes sticking up here on the oscillogram, and little spikes sticking up on the sonogram, and one of the things that people pointed this out in this paper said that this rough frequency profile that you see is actually a characteristic of screams for all sorts of different species, including our own screams. If you picture, a murder mystery and you hear this loud scream in the movie, that scream goes, ah! And I don't know if you can hear the ah. You can hear the modulation of the frequency a little bit, both the volume. There's this jaggedness in character to that scream, and it causes a visceral response in you. You suddenly feel that, and your heart starts to race. And they've seen the same thing with bats. When they hear a distress call, they also become instantly, elevated blood pressure, elevated heart rate. They are ready to do their fight or flight mechanisms, just like you would be when you hear a scream. And it's partly because a scream has a particular signature of this jagged frequency profile. And that's true of bats, and it's true of us. Our next question: are bats affected by the phase of the moon, like a full or a new or a crescent or a half? There's a lot of different light in those. So let's think about that. What direction would you think it would be? Do you think there are more bats when there's a full moon, or more bats when there's a new moon and it's dark? Which direction would be? Commit to yourself which one you think it would be. And how do we figure it out? We, of course, study this with linear regressions, with multiple regressions where we're looking at all the different factors that might contribute to bat activity. And we can make a correlation between the amount of light and bat activity. So a positive correlation means more light means more bats. A negative correlation means when it's brighter and there's more light, there are fewer bats out. And they've calculated the correlation coefficient for different species just in case there's a difference between the way that they react to it. So if you're looking at these, for the most part, these numbers are relatively close to zero. In fact, the big brown bat here is within error of zero. The little brown bat is almost within error of zero on the other side. The other bats along in here are showing a slight negative correlation, meaning that bats don't like to come out very much when it's bright, or there's a little bit preference to avoid the bright lights. And then our hoary bat here is the only one that shows a pretty substantial preference for dark skies. So there may be a difference between these different species here, but let's take a look at a couple of the raw data for this. This is actually a different study, so we're going to look at a variety of different studies here to see how consistent is that result, if at all. So this is the effect of moonlight on little brown bats, where here we have a full moon where it's very bright, and here we have a new moon where it's very dark. And do you see a trend or a pattern in this? Not very much. There are a lot of dots everywhere at different things. You can have a very high amount of bat activity when it's bright. You can have a very high amount of bat activity when it's medium and at half moon. And when there's a new moon, you can also have a reasonably high level of bat activity. So no clear answers there. There's another study here that shows, they claim that it shows that bats like dimmer lights, lunar phobia they call it, and this is their plot showing the percent luminosity versus the abundance of bats. And they put this little circle around here to talk about how extreme full moon nights are the nights when there's the least activity. And I'm not entirely convinced, because I put my little circle around here on the new moon when it's extremely dark, and I also find that activity is below peak levels over there. And I think that they've just simply cherry-picked this small little section over here, and I'm not fully convinced that this is a statistically meaningful setup, even though they do have some statistics in the paper to back it up. But it's a little bit on the vague side if at best. So we're not seeing a super strong signal at the very least. And one more plot here, showing here in dark line, it shows how the bats are out at different times of night. There are no bats at sunset. There's no bats at sunrise, and in between there's more bats. But when it's full moon, this lighter gray curve, in the middle of the night when the moon is directly overhead and it's full, this particular bat species seems to be not around very much. And why might that be? Well, it might have nothing to do with the bats per se, but this paper also showed the number of collected katydids on different nights with different moon illuminations, and it showed that the katydids did not like going out when it was brighter out, and so there's maybe a strong correlation with the way the bats behave, but it has nothing to do with the bats being afraid of the light as much as it is of their food source being afraid of the light, and they know when their food's not out, it's not worth going hunting. So it's quite possible that there is an effect. It's a relatively small one, and it's probably more related to food source availability than it is to the actual moonlight having an impact on the bat's behavior. But that's a great way for us to answer this question with loads of data and trying to use regression functions to pull out meaningful signals from those data among all the other factors and controlling for all the other factors. So learn your multiple regressions. One of your homework assignments for tonight is to do an exit ticket, where I'm going to check and see how much do you remember about what causes sound to get quieter as you get farther from a bat. And remember that we learned about two different things. There's some different effects that are going on, and I want you to write a paragraph that explains those. It should, of course, include that idea of geometric spreading, that sound decreases in intensity as you spread the energy out over a larger surface area. But it also includes this key point that higher frequencies attenuate faster. So they fade out and you don't get to hear them echo back because they're gone. They're turned into thermal energy, the random motions of molecules we learned about last time. Now, if that's the case, if high frequencies attenuate more quickly than low frequencies, why would a bat ever want to use high frequencies? They just fade away. So maybe you can come up with some ideas, and you've got some different options related to maybe the fact that maybe it's so that you can not interfere with your neighbors as they're hunting, or maybe you don't want to hurt your ears, or who knows what it is. But there's definitely some answer to this, because if they didn't have a point in using high frequencies, they wouldn't use them because they don't travel as far, and they could save energy, make less noise if they just simply use lower frequencies. So let's try and dig into this. How will you tell if the bat is closest? If you see a bat pass that looks like this from one of the sonograms, you can see the time going by here in milliseconds and the different frequencies. How will you tell it's closest? Well, you might include things about the intensity of the sound. So the bat is maybe loudest when it's most intense. But what about the frequency content? Does that give us a clue? Let's say some people think that there's going to be the area where the bat is closest is somewhere over here. Let's look at that in a little bit more detail. And of these calls, which of these calls do you think is the one where the bat was closest? Are you going to go with 1, which goes up to the highest frequency of all the ones here, or 4, where it's the highest intensity? And we really see a trade-off here. This one does go to a higher frequency, and if it was closer, those higher frequencies would not attenuate as quickly. This one seems to be really loud, so if there were high frequencies, you'd think that they'd come through. So really, is this the bat changing its frequency range? Or is there something about the physics of sound that would tell us which of these is closer? So let's first just check to make sure. I think we know the answer to this one. Can bats change the frequency that they emit? And we've seen time and time again that they can. Here's an example from even just a single bat flying by, and let's listen to it. Echolocating. You can see it gets to higher and higher frequencies, a larger bandwidth, and then catches a bug and keeps going. This feeding buzz here is really critical for its motion, and it seems to be choosing to use higher frequencies during that feeding buzz than it does when it's out in its search phase. So let's take a little closer look at what goes on during the feeding buzz. This is a video timed with the sound.
As the bat homes in, its squeaks speed up.
There's our moon. So I hope this quick video, seeing how a bat's changing its voice as it attacks, it's changing how rapidly it's making the pulses, it's changing the frequency that they're going at, it's changing how loud they are, and it's doing all of that by intention. So we know bats can change the frequencies that they make. So the question is, why are they choosing to make high frequencies in some times and not others? And the frequency content that we actually end up hearing, it depends upon what the bat chooses to emit, the source, and what happens along the way on the path it takes to get to us through attenuation, and also obstacles that are in the way. And we're going to look at those in detail in just a moment. But basically, if a bat chooses to emit higher frequencies, it's got to help them somehow. And our question is, how does that help them? And again, physics is going to help us understand this. So here's a little picture of some waves traveling down a stream here, and there's a little obstacle in the way. And if you look down here, a little bit after that obstacle, can you tell that there was an obstacle there or not? Can you see the evidence that it was there? Well, maybe it's a little bit disrupted, but overall you still have basically a lot of wave energy still coming even after that little obstacle was there. And so we need to understand this a little bit better, these little ripples along here. And we're going to use something called a ripple tank. And ripple tanks allow us to study how waves interact with each other in objects. They're simply literally little bins of water, and you shine light on them, and you can make these gorgeous waves. And since this is a computer, you're going to have to do a computerized version of it. And I want you to go to this website, falstad.com/ripple, where you can play with a computerized ripple maker and play with that, do all sorts of things, adjust a bunch of stuff, and then reset the simulator by reloading. Set the source frequency to 1 and observe what happens. Just when the waves get to the middle of the screen, are they there? And then stop and clear the waves, and then add a solid box. You'll see there's a little place to add a box in the upper left. Place it a couple of box widths below the source, so near the top of the screen, and observe what happens as you start the waves back up. Stop it, clear those waves out, and then start again with a different source frequency. Instead of 1, go up to 10 and observe. And each time ask yourselves, when the waves get to the middle of the screen, can I see evidence of that box? And this is what it looks like in my screen. So we're going to start off with that long wavelength. That's the low frequency of 1. And we're just going to see what it looks like as it goes through here. I've got these 2 little probes here that show us the amplitude at different points in time. And both of those round to 60. So they're about the same. You can see that as the signal hits the edge of our ripple tank box, some of the energy starts bouncing off. We can get kind of a little bit of deformation. It's not quite a perfect bullseye. And that's important because we want to be able to compare when we add this little tiny box here that's a little bit smaller than this wavelength. What's going to happen? Are we going to see evidence in these probes? Are we going to see evidence in the shapes of the waveforms? Well, let's take a look here. Let's turn it on. Same long wavelength signal, but now there's the box. And when you get to the probes, 62, 62, they both round to 62. They're almost exactly the same. If you look at the black and blue stripes, they're pretty much exactly the same, except right in the spot, right around the box, where you can see that wave is kind of adjusting, but by the time it gets to the next wavelength down, it's completely gone. There's no evidence of that box at all. But let's say if I increase the frequency, I make a much shorter wavelength signal, and now this little box here is much closer to that wavelength. It's actually even bigger than that wavelength, and watch what happens. You can see the energy pulsing off of here, bouncing off and reflecting off of this box. And as it reflects off of the box, that means that the energy doesn't get to the other side, so we see this shadow. And you can notice that reflected in the amplitude. This is 34 over here on the left side where there's no box, and 24 where there is a box. So we've lost a lot of the amplitude because the energy is reflected back. So you can see this box. Either if you're on one side of it, it looks quieter, or if you're on the other side, you're seeing the echo from that box. No echo when you had the longer wavelength. But we can get an echo if we take this box and make it bigger than the wavelength. Let's watch what happens here. Here's that same long wavelength frequency of 1 signal, and now you're starting to see the reflection off of that. And as the energy reflects off, that means it doesn't make it to the other side, so we see the shadow zone, and 57 versus 26. So we've lost a whole lot of energy behind this box. And it's because it no longer is able to make it around to the other side. So put another way, higher frequencies seem to reflect off smaller objects, and lower frequencies go right past smaller objects. Now, why would this be? Well, there's some physics things that you can know. It's called the Huygens principle and explains why small objects don't reflect energy. So I'm going to send a wave through this little tiny slit here. And when you see the energy going through the slit, ignore what goes on up there and just look down below. It looks like this is a new wave source. This little slit, this little opening acts like a brand new wave source with energy spreading out from it. And that's a new little point source. That's called Huygens principle. Well, the same thing is true if we have a corner. Let's watch what happens as these waves get around the corner. You can see it looks a lot like that new point source coming out. And if we have 2 corners going around this box, you'll see the energy curves around from those 2 point sources, and they start to reconnect on the other side. And whether or not they reconnect depends upon how big this box is compared to the wavelength. If you have a really wide box and relative to the wavelength, those waves don't connect very well, and you get this big shadow zone. If you start getting a smaller box that's about the same as the wavelength, you might get almost no shadow zone. And by the time you make a really tiny box, those waves can wrap around and reconnect without even missing a beat. So how big are we talking for these objects and these wavelengths? We need to calculate the wavelength of different frequencies to figure out how big a box we can see. So what's the equation for wavelength? Well, it's wavelength equals speed divided by frequency. And of course, if you have 260 hertz, that's a middle C. The wavelength of that signal is 343 meters per second divided by 260 cycles per second. And so that's a wavelength, that's meters per cycle, of 1.3 meters. So that means that you need to have a really big box in order to block a sound wave. But if you go up to a high frequency sound wave, an ultrasound wave like the bats make at 26 kilohertz, now all of a sudden that equals 0.013 meters. That's 1.3 centimeters. That means that you can reflect a box as small as 1.3 centimeters, and the energy will reflect off, and there'll be a shadow zone behind it. If you want to see something even smaller, like say 8 millimeters, you've got to go up to a frequency like this PAHE at 45 kilohertz, which has a 0.008 meter wavelength. And so in order to resolve an object that is 8 millimeters large, like say a mosquito, you need to use a frequency that's 45 kilohertz or above. And that means that the Mexican freetail, if it's hunting for mosquitoes with these low frequency sounds, those sounds are just going to go right past the mosquitoes and not echo, so the freetail is not going to even be able to see them. So you now should be able to answer, why would a bat make a high frequency sound? Because it wants to eat a small prey. And even more than that, it can go even higher frequencies, and it can see the details in the prey, and not just see approximately how big it is, but it can get some details about its shape. So it can decide, is that a tasty type of bug that's tiny, or a really not tasty bug that's tiny? And it can notice their wings and their wing beats and all sorts of amazing things, but only if the frequency is high enough. And that brings us to our next question that we asked last time, and we didn't get it answered, but now we can finally answer it. What's the purpose of harmonics, like targeting or whatever? And remember, harmonics look like this, where you have the main signal, and then at twice the frequency and 3 times the frequency, you get extra signal coming out. And we talked about last time how a bat does not get to choose to turn on harmonics. It's a feature that has come about by the nature of their vocal cords and their shape of their body, and all of those things working together. And so the question is, why might that have happened evolutionarily speaking? Well, if you're making a noise at this frequency, you get an extra bonus signal at twice that frequency. It's a little bit lower in amplitude usually, but you get this extra signal which is able to show you smaller details. And so you're able to get bonus information from just one signal when you have harmonics. And so it's possible that is one of the reasons why harmonics evolved in certain bat species, is so they could get that extra information without much extra effort. And this has a huge implication for how bats behave. This is a simulator showing what it looks like for a bat to see as things bounce off different size objects. So this 15 here represents an object that's 15 millimeters across, and we can hit echolocate by this Mexican freetail bat. And we can see the original pulse of that Mexican freetail and what signal it sees back. And if we move this object further away, you can see that the horizontal axis down here changes and gets to be longer and longer times of delay, because it's going to take a long time for that signal to get there and get back. And we can see that reflected on the x-axis. But the other thing that we can do is we can actually take this object and we can make it bigger or smaller. And what happens when I make it smaller than, remember, its characteristic frequency has a wavelength of about 1.3 centimeters. And if I make it smaller than 1.3 centimeters, it sends out this signal. And no matter how close this object is, the energy mostly goes right around it. But as soon as I make that object big enough, you can start seeing it. And so if you wanted to be able to see a small object like this, we might need a different bat. We can try this silver-haired bat and echolocate with it, but you can see that its frequency range doesn't go high enough for this tiny little shape. The canyon bat, even the canyon bat is not able to see that object unless it's very close and only with some of its higher frequency components of it. The fringed myotis, which goes up to very high frequencies, is able to see that object fairly well. But take a look at what happens if you go more than about 3 meters away. That signal completely disappears because higher frequencies attenuate so quickly. And so you can start seeing all of these behaviors. And I encourage you to play around with the simulator to see what does a bat see. And you can add in multiple objects and multiple shapes. And it's useful to try and see here if we try and play with, say, a couple objects that are at different distances. So if we take a single pulse here, how long is this signal that the Mexican freetail makes? It's about almost 20 milliseconds there. But can you make it look longer than 20 milliseconds? You can by bringing another object that sound echoes off that's taking a slightly longer path, and you can make it last almost twice as long. Or you can change where is the most intense energy. Is the most intense energy at the beginning of the call or in the middle of the call? Well, in the original Mexican freetail, most of its energy comes at the beginning of the call. But because we have sound bouncing off of two objects, if we were to have our own microphone record that, we'd see the energy in the middle of the call, and that doesn't look like a Mexican freetail bat. That looks like a different type of bat. That's more characteristic of our silver-haired bats, which look like this. And if you take that far enough away, you don't see the higher frequency component of the silver hair because higher frequencies attenuate faster. And so you end up seeing something and you get confused. Is it a silver hair or is it a Mexican freetail? You won't be able to tell because of that extra echo that was causing problems. So extra echoes is what we want to talk about right now. So when you're looking at another animal like a bird and you want to observe it, we know that the recording conditions can obscure details. Like, can you tell what type of bird this one is here? No, because there's stuff in the way and it makes it hard for us to see it. Or this one over here is blurry. It makes it hard for us to see. So we have the same problems when we're looking at echolocation calls trying to interpret the signals of bats. And we need to remember that shorter wavelengths bounce off tiny objects. So if we were to look at a bat and we were to record its signal with a microphone held in our hand, well, with a bird song that would make, if it was to go through here and touch this tree, the leaves, those are all smaller than a meter. The branches, all smaller than a meter, and so those signals would go right through. But with a bat's echolocation call, they bounce off because some of those leaves are bigger than a centimeter, and so they're going to have energy bouncing off. And likewise, energy bouncing off the ground, bouncing off a person's body. We have all these echoes coming in because high-frequency short wavelength sounds can bounce off of really tiny objects and lots of really tiny objects. And so we end up with lots of signals arriving at one time. And if we sort of fold a bunch of those signals out here, what we end up with is that if we have our main signal arriving like this, well, our next one might be a little bit smaller amplitude but it also took a longer path, so it's a little bit later. And then there's another signal that comes in from a slightly longer path. But when you bring all those three together, you get something that looks really long. How can we avoid that? Because we want to be able to see what the actual call looks like, not the smudged together with all of the call and it's all these extra echoes. Well, what if we took the microphone and moved it up higher instead? Now, when we look at those echoes that are coming and hitting it, we have the original call, and we have those echoes. They're still coming, but they're a little bit dimmer because they've traveled a longer distance to get all the way up to that microphone, and they're delayed by a substantial amount. So now when you smudge all those things together, they actually don't obscure each other. You can see the main signal, plus you can see some of those echoes, but they're all dispersed from each other, and so the echoes are softer and separated, whereas here the echoes are loud and they overlap with the original call. And this really affects what we see in our microphones. So we have, let's say, a signal here, and our microphone is down near the ground. Well, if that was the case, we get all these echoes from all these different directions that all take slightly different length paths and have slightly different amplitudes. And when you add them up, remember, we can get signals that are constructively interfering and destructively interfering, and you end up with what we call acoustic mush, which is basically a whole bunch of messy signal, and we can't see the original call very well because it's obscured by all the extra signals that are arriving at the same time. Now, let's say you're not over a rough ground surface. Let's say you have your bat flying over water, which is a nice, smooth, mirror-like surface. And here you might only get one extra echo. And that here this is called specular reflection, and those echoes also interfere with the original signal. You often get these comb filtering like effects where you have these cute little things that kind of look like fish bones or a comb, and they're cute because they look nice, but they're really bad for identifying bats because it's hard to see the information of the original call. And how bad does this get? Well, we have a quick simulation or a quick experiment that we did where we put one microphone right down here at a little bit above eye level and one up on a pole way high above it. And we're going to look at the signals for those two that were recorded from real bats flying by and try and see what they look like. And so you're going to be looking at some pages that have real-time, compressed, and a single call for the microphone that was up high and the one that was down low. But I'm not going to tell you which one is which. You're going to have to try and figure it out. And the first thing you need to do is try and figure out, are you looking at the same bat pass? And if you do that, which pages are you going to compare? Are you going to do the real time, the compressed ones, or the single call? Then you have to guess which one was up high and which one was down low. And within both of those combinations or both of those microphone setups, can you spot the specular reflections? Can you spot the acoustic mush? So the PDF is in the comments for the YouTube video here, and you'll be able to view it yourself and look through all of those different signals. And we did this in real life in a beautiful spot up in the Sierras. This is at nighttime where there's a microphone that was way up here at 4 meters and another one that's right here on this pole that's only 1 meter off the ground. And let's see some signals from those two. So here's a comparison of the same sequence. You can see these look like they're pretty similar in character and everything. But if you look closely at them, here is one of those signals from up high. And here is one down low. Can you spot the acoustic mush? Look what it does to the oscillogram and the shape of the energy distribution in that call. Here's another one, and because of the way Sonobat's compressed view moves things around, when you have a lot of acoustic mush, it also it makes it so that it takes up extra space in the compressed view. And so I had to sort of slice up my view to show these calls one by one by one from another pass of a different bat. And take a look here. You can really see how much mush there is in that microphone that's down near the ground compared to the one that's up high. So what is your take-home message from all this? Put your microphone up high so that you do not have to deal with overlapping signals and mush and all of those terrible things that make it hard for us to interpret our sonograms. So how high? Well, you read in your reading that you should be going up as high as 4 meters is a great height, but higher is always better. Practically speaking, whether you're at 1 versus 2, 2 versus 3, 3 versus 4, you're always going to get some improvement as you go up higher so you can get avoiding all of the echoes off the ground. So remember, put your microphone up high.